Welcome to today's Explainer. Today, we're unpacking the foundational logic that powers the modern digital world. We're opening up the architect's toolkit and focusing entirely on the magic of nonlinear data structures, specifically trees and graphs. If you've ever wanted to understand how your computer thinks beyond a simple boring checklist, well, you are in exactly the right place.
Okay, let's dive into this. Have you ever actually stopped to think about how massive tech platforms organize, well, an almost infinite amount of information? Just imagine the bottleneck, the absolute nightmare of searching through modern databases if we only relied on basic sequential lists. If you had to search a billion users on a social network, one by one from top to bottom, yeah, your search would time out way before you even got close. That right there is the fundamental problem software engineers face every single day.
So to solve that bottleneck, we have to completely abandon linear data. Think of linear data like a grocery list, stored in consecutive order. It's great for simple tasks, sure, but it absolutely does not scale. Instead, we need nonlinear data structures. This is where things get complex, branching, and interconnected. Establishing this core conflict is crucial, because to solve today's massive computational problems, that old sequential approach, it simply had to be abandoned for something much more dynamic.
Here's our roadmap for this explainer. First, we'll look at moving beyond linear data structures. Second, we're branching out with trees. Third, navigating the graph network. And finally, designing for emerging tech.
Section 1. Beyond linear data structures.
Modern system functionalities, from your GPS down to the search engines you use every single day, they require a massive leap beyond standard arrays and lists. This leap is the nonlinear data structure. Basically, it's a format where data elements aren't arranged sequentially or linearly. Instead, they allow for complex, hierarchical, and interconnected relationships. Grasping this overarching concept is totally vital, because this foundational shift is exactly what allows developers to explore radical design alternatives that are frankly impossible with just a straight line of data.
Section 2. Branching out with trees.
Now, what's really interesting about this slide is how it visualizes these concepts. When we talk about hierarchical relationships in computer science, the tree is the ultimate structural metaphor. Think of it exactly like a massive corporate org chart. The individual data points, or employees, are called nodes. The reporting lines connecting them? Those are edges. The CEO at the very top, where everything begins, is the root. The route you take from one node to another is the path, and the longest path from the root down to a leaf, the bottommost node, determines the overall height of the tree. When you see it mapped out like this, you can see how data branches out perfectly.
But, having this beautiful tree structure is completely useless if we don't actually know how to navigate it, which we call traversal. For binary trees, where each node maxes out at 2 children, we have 3 rapid-fire ways to explore. In order visits the left branch, then the parent node, then the right. Post-order hits the left, then the right, and saves the parent for last. And pre-order grabs the parent first before diving down the left and right branches. Distinctly separating these methods is what allows a system to execute tasks with absolute pinpoint accuracy.
And of course, engineers are always optimizing. That's where threaded binary trees and binary search trees come into play. A binary search tree neatly organizes smaller values to the left and larger values to the right, which literally cuts search times in half with every single step. Threaded trees go a step further by utilizing empty memory pointers to create sneaky shortcuts back to other nodes. These are really specific design solutions built purely for faster, leaner system operations.
Sometimes, though, you're stuck with a massive general tree where a node might have dozens of branches, and you really need to convert it into a sleek binary tree. It's kind of like a clever engineering trick. First, just identify your general tree structure. Then, draw a link through all the siblings. Those are the nodes sharing the same parent. Next, remove the links from the parent to all children except the very first one on the left. Finally, rotate the whole resulting structure 45 degrees. And just like that, boom, you've elegantly optimized your structure.
But let me ask you to think like an engineer for a second. What happens when a tree gets violently unbalanced? Just imagine a massive influx of data where every new number is larger than the last. Your beautifully branching tree suddenly turns into a long, lopsided sequential line, which completely defeats the whole purpose of a nonlinear structure. Your search times would absolutely crash.
Enter the hero of our story, the AVL tree. The AVL tree is a self-balancing binary search tree. When data comes flooding in, it enforces balancing constraints. It implements height balancing and manages weight balancing. If an insertion or deletion case threatens to make the tree lopsided, the AVL tree literally rotates its nodes automatically to keep the height difference between its left and right sides perfectly in check. It completely fixes the limitations of basic binary trees.
If you want to see this elegance in action, try implementing an AVL or a B+ tree in your next side project. Coding out those insertion and deletion rotations yourself is a mind-bending way to appreciate the architecture. It really truly locks in all the mechanics we're talking about right now.
Section 3. Navigating the graph network.
So, if trees are corporate ladders, graphs are massive, interconnected webs, much like a complex city transit system where basically everything can connect to everything else. A graph is a network composed of those familiar nodes and edges. We measure nodes by their degree, which is simply the number of connections they have, and by the paths between points. Now, while graphs share terminology with trees, the major difference is that graphs actually allow for closed loops, cycles, and just massive webs of interconnectedness. This makes them a fundamentally different design alternative.
And this brilliantly illustrates how a computer actually sees all this. To a machine, a graph isn't a bunch of floating circles and lines. It's a matrix, a grid of ones and zeros. A 1 indicates an edge exists between two nodes, and a 0 means there's no direct path. It's an incredibly efficient way for software to map out really complex relationships numerically.
Navigating these graphs requires specific elementary operations, primarily breadth-first search, or BFS, and depth-first search, or DFS. BFS explores the graph layer by layer, checking all immediate neighbors first, which is perfect for finding the shortest path on unweighted maps. DFS, on the other hand, plunges as deep as possible down a single path before backtracking, which is absolutely incredible for solving puzzles or mazes. Developers are constantly choosing between these two based on specific problem constraints.
A massive application of graph traversal is routing. Say you're designing flight paths for an airline. You need the most efficient route connecting all cities. First, you analyze the full graph network. Then you identify the shortest paths between key nodes. Finally, you construct what's called a minimum spanning tree, or MST. An MST is basically a subset of the graph that connects all the nodes together without any cycles using the minimum possible total edge weight. It is a strictly critical skill for optimizing any kind of physical or digital network.
Section 4. Designing for emerging tech.
To truly design for emerging tech, we have to evaluate the ultimate architect's choice. You see, every single nonlinear data structure has inherent trade-offs. The benefits are massive: rapid search, scalable hierarchies, and incredibly efficient routing. But you have to identify the limitations: high memory overhead, incredibly complex insertion and deletion mechanics, and the constant processing overhead required to keep structures like AVL trees balanced. You always have to weigh these against the specific problem you're trying to solve.
Ultimately, the goal here isn't just memorizing terms like nodes and edges. It's the ability to synthesize knowledge about a problem to reach appropriate conclusions. It's really about intelligently evaluating your constraints to design the absolute best possible architectural solution for the data you're handling.
So the crucial point is that recognizing these data structures is essential to new developments in emerging technologies. Trees and graphs aren't just academic theory, right? They empower the complex decision trees used in artificial intelligence. They're the exact structures optimizing massive social network graphs to show you relevant content. They drive the shortest path routing in autonomous navigation systems, and they create the structure needed to query vast, incredibly deep, big data lakes. Literally everything from modern AI to the apps on your phone relies on the sheer elegance of these branching and interconnected maps. Which leaves me with one final thought for you to chew on. How will you use these ancient mathematical concepts to map out the future of technology? Thank you so much for joining me on this explainer. Keep learning, keep building, and I'll catch you in the next one.